Okay, guys, we are live. So, hello everyone, and welcome to our webinar series. And surprise, surprise, this is the Zenoh 1.0 Unveiling, the first episode. And today I'm, let's say, in order with Julien.
Julien, hello everyone.
Everyone knows you, but in any case, for those few people in the world that don't know you, do you mind introducing yourself?
Yes, Julien Enoch, Solution Architect at ZettaScale, and taking care of Zenoh plugins, and more specifically for the robotic domains, also involved in RMW Zenoh projects that I will talk about today.
Very good. Luca, likewise for you, and don't forget to introduce.
So, hi everyone, I'm Luca Cominardi. I'm the head of technology for the Zenoh project. So I look after the R&D activities for Zenoh. And I was together with the whole Zenoh teams working hard for this 1.0 release for Zenoh.
Okay, very good. And I'm hosting the webinar series, Angelo Corsaro, CEO and CTO for ZettaScale. So what I'm going to do now, I'm going to share my screen and we're going to start this webinar. So let's see. So you guys should be seeing the screen immediately. And I think that it's also worth mentioning that this series, we will try to pull in as many members of the team as possible to cover the various different aspects of the Zenoh 1.0. And where I would like to start with is with a retrospective, because it's a young protocol, but quite a few things have happened. And it's always good, especially for those of you that maybe joined while the train was already running, to know where we're coming from and perhaps why we did Zenoh, right? And in fact, that should be the first question. Why on earth did we decide to design a new protocol? I mean, that's crazy because it's a lot of work, right? Isn't it? And so, I mean, there were some technical objectives. There were some, I would say, non-technical objectives. But let's start with the technical objectives. Before starting Zenoh, I think an increasing level of frustration had grown on us with respect to the fact that the system that our customer was trying to build were more and more spanning from the microcontroller up to the data center. So if you recall, we were working in smart city like Nice in Barcelona, in some, let's say, industrial application. And immediately you struggle with a very basic problem, which is like the 101 of data communication, which is letting data flow from the small microcontroller, the small sensor, up to wherever you need it. And to do that, we had to hook together several different protocols. That was already one of the challenges. And nobody seemed to care.
Yeah, it was a bunch of integration made by a lot of companies for this. But
a system integrator makes a lot of money out of it. It's great for them, right?
For them, but still.
And I mean, to us, we used to call that the digital Frankenstein, the ugly digital Frankenstein. And that was one problem. Then something else that was pretty severe was each time, especially in Barcelona, we wanted to keep data decentralized. It was very, very hard to do it because you have to keep track of where it's stored. And once again, you get in troubles. And so we decided at some point, enough is enough. Nobody seems to be bothered by this. How about, we try to solve this problem. And so we said, okay, let's try to design a protocol from scratch, starting from all the experience we have done in this system and in designing other protocol. And let's try to have a protocol that can run efficiently in time and space from the microcontroller up to the data center. And the original goal was to make sure that we could move data around, but also do distributed queries, so that on theory, you could keep your data stored wherever in the system and query it from anywhere without knowing where the data was. And eventually, we managed also to represent distributed computation, which was like the cherry on the cake. Notice that as a consequence of wanting to run from the microcontroller up to the data center, it was necessary to be able to run at level 2, so at Mach 11 upward. We didn't want to have topological constraint because there isn't one topology that cuts it all. And many technology, MQTT, Kafka, DDS, they decide a topology for you. So they pick an abstraction, which has nothing to do with topological constraint, and then to implement that abstraction, as we will see, impose a topological limitation that then has deep architectural consequences on your system. If you look at API, programmers enjoy good API. Not all API are necessarily great. Everyone makes mistakes. We do also. And the big difference is not about not making mistakes, but it's about recognizing your mistakes, recognizing that now you have a deeper understanding and fixing those so that you improve your API, you make them more orthogonal and so on and so forth. And I guess, Luca, you will share quite a bit about that on your section. Security and performance are also important. I mean, everyone now talks about C++ and memory management issue causing 70% of security problems, but that was already known back then, right, to those who looked for the right information. As a consequence, the decision to use safe programming languages. And ease of integration, because no protocol is an island. As soon as a protocol exists, in some sense, it's already a legacy that has to interoperate and integrate with other things. So we wanted to facilitate that. And then there is another interesting requirement, because back then, right, we were having some investigation into some smart grid application. There was also, I don't know if do you recall the COW project?
Not this one.
Coalition of the Willings.
Ah, yes.
You do?
Exactly, yes.
So that was a smart grid project in US,
Yes,
right? Yeah. In which essentially, in order to be able to replace, in some instances, Modbus TCP, we needed a solution that had a wire protocol overhead that was lower than 7 bytes. Why 7 bytes? Very simple. Modbus, that overhead is 7 bytes, and many of these companies pay by byte. So if you deploy something that takes more, you're going to increase your bill. Not possible. And then there were some non-technical objectives, and I think those were coming from our frustration and I would say, kind of being fed up with traditional standardization organization or designed by committee, okay? So we wanted to make sure that if we do something, there is a governance that promotes meritocracy, technical innovation, quality, and openness. That what we do is, as an open design, it's open source, and has a very open community. And as opposed to write, hundreds of pages of spec, just make sure that you have code that works first and that is proven in the field before you even consider writing a spec, because the other way around, has proven to be the source of many problems. Okay, so with that, we did Zenoh. And by the way, for those of you that don't know Zenoh, I will have a small introduction. Those that know Zenoh, bear with me a couple of minutes, but we couldn't just avoid a quick introduction on Zenoh. So Zenoh is the result of this effort that we started, as we'll see, several years ago. And it is a pub sub query protocol. So many people that approach Zenoh, sometimes they are attracted by the pub sub because of its simplicity, its performance, its flexibility. But the real power of Zenoh stems from the fact that we have this combined abstraction of distributed pub sub and distributed query that are used, again, for querying databases, but for triggering computation. And as you will show, that's heavily used, for instance, in ROS, right? And we unify all of these, as we'll see, in a very elegant, nice API that keeps getting cleaner and cleaner. Zenoh is able to run, as we have seen, from embedded up to the data center. Everything is location transparent. And we have support. We've had support for zero copy and shared memory for quite some time, with some updates in v1.0 that we'll discuss in depth in upcoming webinar. Now, something that sometimes I think is underestimated is the fact that as a protocol, Zenoh provides a universal abstraction. If you think for a moment, when you build a distributed system, usually you have a data plane, a control plane, and a management plane. And for building data plane, pub sub, usually it's what you want most of the time, right? Most of the time, because the abstraction works, then sometimes it's the implementation, because perhaps I can't always pull data, okay? Push data. Maybe I want to pull or I want to have some other mechanism. But as an abstraction, that works quite well. Then if you try to build a control or a management plane just using pub sub, like people using DDS, that's where the pain starts, right? Because you need some form, some way of getting information, so issuing query literally, right? And some mechanism for triggering computations. And the nice things of Zenoh is that a single protocol provides you with, primitives that allow you to cover all those use cases. You can do pub sub, you can do remote computation, you can represent storages. In fact, we have plugin for several storages and have distributed queries. So one protocol from the microcontroller up to the data center that has all the primitive that you need to build distributed system. That's very powerful,
and
guys.
in an efficient way, in a very efficient way with regard to building PubSub over to build query subscriber over publication subscriber.
And again, I mean, if we think other technology, you would have to combine a PubSub with something else, right? To do for instance, RPC. And something else, we have endless discussion because I never want query to be called RPC. Why? Because RPC is client server, right? I have a server. I need to know where the server is and usually issue a request. Our query, it's a generalization of that mechanism that is also location transparent, right? Which is super powerful.
And to have all of this, I mean, we mentioned in the previous slides, embedded microcontrollers.
It's incredible.
So it's not only that we can bundle all of this together, but we can make it fit in a device as small as an Arduino.
Yeah. And then the concept of transparency, it's powerful because, for instance, when you do a get, right, you have no clue if the data that you're receiving, well, first of all, from where it's retrieved and whether it was a result of triggering computation or querying some databases or some data source, which is very powerful because all of a sudden I can decide whether I want to store some data, compute and store, compute on the fly, and that doesn't at all impact the application that is actually interested in consuming that data. It's quite powerful. Okay, so as we mentioned before, it runs everywhere. You can run from data link upward. We support plenty of transport that actually in Zenoh terms are called linked in this case, TCP, UDP, quick serial, you name it, okay? And if you want to add another one, you can. Your favorite programming language is highly likely to be supported, and if it isn't, contribute it, or maybe it's in our roadmap, but you go from Rust, C++ to Python, TypeScript, up to programming languages like Kotlin, not forgetting that everything you do in Rust, you can also do with REST, for instance, which is very powerful. I will never be tired to say we have built-in shared memory and zero copy support that doesn't have any external dependency. That's built in the protocol. Zenoh understands that and optimize for it. So we'll perhaps, you will learn more on next webinar. So 1 week from now, when we will cover shared memory. No topological restriction. So communication can happen peer-to-peer, over a click, over a mesh. You can have clients that use peer to route their communication. You can have software routers. And once again, software routers are very lightweight. We always discuss what is the difference between a peer and a router. And V1 becomes even fancier. And I think the good classification is that a router, you have to consider it as something that is part of your infrastructure. So it's really a question of boundaries, okay? But from a functional perspective, you can have, as we will see, plugin in the router as you have in the peers, and then no topological constraint. To put it in perspective, right, if we just constrain our reflection to PubSub, DDS provides PubSub, MQTT provides PubSub abstraction, Zenoh provides PubSub abstraction. So from an abstraction perspective, right, they provide an equivalent abstraction with respect to PubSub. But then MQTT and DDS impose over you topological constraint, whereby MQTT decides that you can only communicate through a broker, which is problematic because the question is, where do I deploy the broker? In the cloud, right?
What if it fails?
What if it fails, right? I get stuck into a proprietary technology, right? And DDS decides for you that the communication model is peer-to-peer, where every peer talks directly with every other peer. And, that has other consequences, right, in terms of scalability, in terms of, especially with the dependencies on UDP, how do I run over the internet, and so on and so forth. Zenoh removes all those dependencies. You decide the topology that makes sense in your segment, right, which is super important. Plugins, and we are going to cover this through the series, but again, it's important to know that Zenoh was designed from day one to make sure that it would be easy to integrate other technologies. And we have seen how successful that was in the context of ROS, first with the DDS plugin, then with the ROS2 plugin, which we'll discuss further. But we have plugin for MQTT and so on and so forth. And likewise, we have plugin for storage. So storages can be added, and here you have the list of what we support, from Amazon S3 to InfluxDB, or even file system, main memory, and so on. Performance. This is actually an independent benchmark from NTU that shows that Zenoh performance are actually quite incredible, because on the 100 gigabit network, we are very, very close to what iPerf gets, right, across the network. There is a paper online that you're welcome to read, a scientific publication. And in short, notice that the y-axis is logarithmic, but you will see that Zenoh has around 3.3 times higher throughput than DDS, 23 times higher than Kafka, 35 times higher than MQTT. If you forget even the bad behavior for packets that are bigger than 64K. And the latency is actually very good. And by the way, you can now also enable the ultra low latency that transport that further reduce that latency to the same level of Pico roughly. Okay, so with that in mind, how did we get here? That's a nice story.
A long one.
And well, not long. It depends on perspective, yes. Right? Because in the lifetime of the universe, what are we?
Just 4 years.
Exactly. It's nothing, right? But it's still impressive. And it's impressive when you reconstruct. So here you see also the transition from the original logo of Zenoh that was definitely designed in-house, right? Yeah. Up to the actual logo of Zenoh, and year by year the evolution. So the first official release of Zenoh, the Rust base, right, was 0.5.0 and was called ITUSA. And by the way, some of you might figure out at some point what are the various different rules that there are in naming Zenoh release. If you figure out exactly what are the rules, I don't know if you have enough data point, you'll win a Zenoh t-shirt, okay? Post your answer on Discord. If you're a geek, you will enjoy how we do it, but I think you'll need at least everyone to get a further hint, right? But anyway. So, but getting back to the releases, ITUSA, which by the way was the Merlin Wizard dragon, baby dragon, was our first release. It was the first Rust version, because before that we had the OCaml version, right? So you had the Rust API, you already had router, peers, and client. We already had the DDS plugin, by the way. Yeah. That was one of the very first, right, that we developed. And there was already quite a few plugins in Flux, Rocks, and so on and so forth.
Yeah, for the storage,
2 years after, and that, the team had started growing. I mean, we had quite some additions. And 2 years after, right, we had started working in a CAPI that eventually, right, became Zenoh Pico. And Zenoh Pico is our our Zenoh implementation that targets really small devices, as we'll see in the very last webinar of this series. Arduino ESP32. I mean, where doesn't it run, right? Pretty much anywhere. We introduced the Python API, the C API also for the Zenoh Rust. Then we moved to JSON 5 and YAML config, new routing algorithm, because we moved to link state there. Yeah. Improved performance. We increased performance by factor 4 roughly from the previous release. And we had the first implementation of zero copy and shared memory allocators. Support for serial and Unix socket transport was also added back then. Then we moved 1 year after to Charmander. And there we had our first C++ API, mutual TLS and mutual TLS. We added query payload. So query payload was something that we always wanted to put in, right? Everyone was asking for it. We didn't have the time because there were so many things to do. But in the first two versions of Zenoh, the payload were passed as argument
in the selector.
In the selector, which is okay, if you have a few arguments. But suppose that I'm a car moving or a robot, and I want to do a query to an analytics that is running on the edge to classify an image. UU encode or base64 encode, it isn't. You can do it, but it's kind of painful. And so we added attachment to support, among other things, those use cases. And I think that made quite a few users very happy.
Yes.
We introduced the MQTT plugin.
Also, It was the very first version.
Exactly. ROS 1 bridge. And that was as a result of the ROS conference, right, in Japan, because many people were asking. And so we introduced that. liveliness token, which we have covered, for instance, in the latest Zenoh tutorial, quite powerful, heavily used in ROS.
Very important.
Yeah. AWS S3 plugin, and that was a request actually coming from AWS. Transport whitelisting, so that was quite important, right?
To ensure that only the configured link protocol like TCP, UDP are used and not fallbacking
on the decided interface, selected interface. Key expression formatters to ensure that you can't mess up or accidentally miswrite or misspell one of your key expression. And then it was the first version of Zenoh C that was compliant with Misera. I think we had essentially the bulk of Misera requirements addressed. And by the way, was the first release of our Zenoh Flow. Okay, it's already, well, in fact, 1 year old, not that old. Then Dragonite, October 2023, we had essentially a Rust workshop plugin, Kotlin, that was the first release of Kotlin. Kotlin with, let's say, non-official support for Android yet, right? Because that came the release after. The ultra latency transport, some core protocol extension that we started, right? To prepare the world over V1, and the quick transport. And then we had the latest release, Electrode, May 2024, where we rolled out Android support. And I think we featured quite a few Android applications. I don't know how many of you have seen, for instance, the real-time tracking that we did sometimes back for motorcycle or cars. Java API, the ROS2 plugin, right?
New version dedicated to ROS2.
Exactly. And that was released because it was already developed before. InfluxDB v2 plugin, we ported to Tokyo. What a bloodbath.
Yeah. And we will see also something else that for 1.0 to deal with.
Exactly. So porting to Tokyo, support for attachment. So you can attach data also now to put operation. And there are lots of cool uses for those. But one, for instance, in automotive is end-to-end protection. But you can attach any kind of metadata, right? So quite powerful. Access control, or let's say we started rolling in access control and downsampling, and those are using a mechanism that was introduced in that version, which were the routing interceptors, which is a mechanism that is available to all of you, transparent compression, and VSOC transports. Okay, so this is it's a lot already, right?
Already.
Yeah, and I mean, it felt to be more than 4 years for the amount of things that we have been doing and collaborating.
It was indeed intense. And so these are some of the statistics, because it's nice to see how the amount of code that has been contributed year over year, which is quite impressive. So this is for Zenoh. This is for Zenoh Pico. Okay, so quite a bit of.
We're seeing here.
So every year.
Rust.
That's for Zenoh Rust. So you have the name of the repository on top. You see. So that's for Zenoh. Every year, then you see from the beginning to the end of the year the total contribution, and then you will see some impact on code that is changed, updated. That's quite normal for a project.
Number of lines of codes.
Okay. Exactly. Total number of code contributed. That's not necessarily the total number of code that we have in our repository.
Contribution.
That's the amount of work that we have done, which is massive.
Yeah.
Okay, it's really massive. And to put it into perspective, Zenoh today is composed of 27 repositories, because we have the two core technology repositories, Zenoh and Zenoh Pico, right? And then all the Zenoh ecosystem, connectors, right, for databases,
and
for
no CI testing,
API bindings, right? 27 databases. That totals to close to 300,000 logical line of code. That's quite a bit, okay? And it's nice because you see that in the end, the protocol is simple. If you look at Zenoh Pico, the core is around 10,000 line of code. Yeah. But then it's the testing and all the ecosystem around. Likewise, so and all the API. So it has been quite of a ride. And again, So then the number of members on Discord has been growing quite quickly, accelerating in the last year. So we are at over 1,100 today. And the other interesting thing is that last publication on Zenoh was a couple of days ago. But we have almost one publication per month. So it's around 10 scientific publications on Zenoh per year, identifying Zenoh advantages in this or that use case and so on and so forth. most of the time in robotics, but not only, right? Which is, we've had robotics, we have automotive, quite a few additional domains, which is nice, right? And let's see, which were the key milestone in terms of adoption and recognition. So in 2022, for instance, the ITU, as a result of a 2-year project trying to identify the protocol to use in intelligent transport system, actually selected Zenoh, if you guys recall, for addressing the
V2X.
V2X, but more importantly, there was one use case, the digital witness, that they couldn't address or solve with other technology. And a distributed query was perfect for that.
Yeah.
So that was the recommendation. Obviously, ITU involves nations. It's a long progress. But now there is a second phase that should actually, it's ongoing. And so hopefully we'll see this coming up to a standard sometime soon. In October 2022, Zenoh, which was an Eclipse IoT and Edge project, was adopted by Eclipse SDV, which, by the way, is today one of the biggest SDV open source working group in the world, and where the GOTA of automotive is, right? GM, BMW, Porsche, I mean, a little bit of everything, Continental, yeah. In January 2023, General Motors decides to integrate and select Zenoh as part of U protocol. And in September, there is the famous R&W alternate report, right, that identified Zenoh as the protocol, right, to go for the alternate RMW, because based on the both the poll on the community and the evaluation of various protocols, it comes on top, right? And I will show you a snip of that. Then there is something in December that actually also happened the previous year, but it's an award to ZettaScale, but really related to the work that we do on Zenoh. So we are considered like a startup to watch in V2X, but because of Zenoh. Spring 50, most innovative startup, once again, because of Zenoh. And finally, right, one of the Zenoh offsprings, Zenoh Flow, makes it to a top-level project, becoming an SDV project, right? Not anymore a child, but the child makes up his own family, which is very nice. That's what we like to see. Exactly. Providing now a pretty cool data flow programming framework for automotive and any other kind of application that might be relevant. And by the way, if you guys join the dots, Zenoh is end-to-end microcontrol to the data center. All of a sudden, you can have data flow that have the same span, which is super powerful. So this is just a snapshot of the evaluation of the RMW alternate, but that's available online. And moving real quickly to Zenoh 1.0. So what 1.0 means, and why did we take so much time? Well, we took so much time because we wanted, as we discussed before, freedom to learn from deployments, from user, from running code, and code that has been running for years. And we have learned a lot. Always remaining humble, we've made changes to improve, to address the new use cases, and now we feel ready to give some guarantees back to the community, which is one interoperability between 1.x.star version, no API breaking changes across any major version. Okay. In addition, 1.0, like 0.11, because 0.11 was our first Eclipse release, and that was a kind of dry run. Make sure that you have IP and licenses review done by Eclipse, which provides quite a few guarantees with respect to the use of the open source. No bad surprises, right? So what's new, real quickly, because you'll do a deep dive. API, lots of work on API, right? Consistency, harmonization, coverage, and new API that will be coming up. Protocol. So as you guys have seen in the evolution, we started rolling some changes that actually broke wide interoperability across the past releases, and those were in preparation for V1 to address again future extensibility and a few things that we have learned. And there are some also improvement on scheduling. We moved to Tokyo. Oops. More on that later. Yes. Yeah. I mean, we're happy, right? But obviously, the asynchronous framework is a key element, and the behavior between async and Tokyo isn't exactly the same, which I mean, it's addressed now, but more later on this webinar. We introduce a new shared memory subsystem. And I think the key things to understand is that with this new shared memory, you can have shared memory even on mesh topologies, which you couldn't before, because before we could only do shared memory if you were on a click, right? You can have shared memory providers, so you can plug your own hardware. We have already users that have done that. And you can support arbitrary layout and canaries, okay? So that's to detect, for instance, overruns from misbehaving applications. Access control, we finalized what introduced in 0.11. And we are doing lots of preparation work to support the release of the Zenoh RMW, and we will discuss that. And preparation isn't only technical. I mean, there has been a huge effort in ensuring that all the testing, the regression, all the testing. But so there has been quite some work, but happy to support that community. Besides what we're doing in the community, ZettaScale, along with the Eclipse Zenoh 1.0, will be releasing also a new version of the pass, where we will have new graph rendering, which is quite nice. ROS2 system browsing support. I mean, can you imagine that? From the past, sitting from the other side of the world, you can discover your robots across the internet and reconstruct the ROS graph.
Yes, list the topic, list the services, and so
Isn't that cool? And with our Zeta tool, you will be able to do that also if you are on the same network or with an offline tool, either locally or remotely. But likewise for DDS support. So the same will be true for DDS support. And we're adding also Kubernetes support. You will be able to provision any Kubernetes cluster from our platform. And with that said, Luca, how about you give us a little bit of a sneak peek?
Yeah, so what I'm going to cover now is just a highlight, kind of pinpointing on the main changes. Along with the 1.0 release, we'll also be releasing a blog post, and we just released also a migration guide. We need to guide all the developers to port to the new API. So why the new API? What is one of the main drivers that is also behind the changes that we've got also in the API? Stability. 1.0 we've seen is a major release. We're going to provide stability and future backward compatibility in such a way we can add more features in the future without breaking existing API. But as well, we want to keep the freedom to keep optimizing our Zenoh implementation, how big our code base is, how memory layout, without breaking the user API. On this point, we have been moving from the 0.11 to 1.0 towards accessor. Okay, what I'm covering here, what you see on the screen is some Rust example, but this is the same paradigm that we have adopted for all bindings. So Rust, C, C++, Python, Kotlin, you name it. So we want to encapsulate and really separate the API from the internal implementation. So we can keep improving things, memory layout, internal optimization without breaking user code. So you will get all the benefits for free. You just need to update your Zenoh version and your own business. There are some minor changes really for the code, like accessor, like in Rust, it's just a matter of keeping on this instead of accessing by field.
No. And in fact, you said new API, but in fact it's updated.
This is updated API. Okay, so especially for Rust, we got some really improvement that is quite extensive, specific for C and C++. We're going to see later. But for what concerns specifically Rust, is really minor change, but a lot of reorganization internally to make sure that in the future we can add everything without breaking user code. One of the biggest changes that we have introduced in 1.0, and we had endless discussion on this bloody value that is return and used in Zenoh. Until 0.11, what we had a value that basically is considered as a tuple of a payload, so some bytes that are carried over Zenoh and received, for example, published by a publisher and received by a subscriber, or, for example, to be published inside a query payload or attachment or everything that relates to user code. We had a value. A value is bytes plus encoding. Encoding in Zenoh is some metadata. So why we decided to change, and why what is really the change looks like. The value, since the value contains also the encoding, from the API perspective, you could infer that to the type. The drawback of this that you have seen from multiple use cases, users, is that most of the times users that are building closed system, they know a priori what the encoding, how they should treat their data, how they should decode it. And as a drawback of using the values, that we are always sending the encoding on the bytes. We couldn't really distinguish from whether we need it or we don't need it. And if you remember the 7 bytes requirements, that is kind of a hard requirement for certain systems, will become quite hard to support it if we automatically were adding some overhead. So we decided to split it, to remove the value, and to explicitly keep a new type that we call Z bytes, that is basically user payload, okay, and to separate it with encoding. At Z bytes, we had also a lot of discussion on this, and I've seen also a bit of confusion on what type of Zenoh can carry or can publish. There are a few users on Discord, on the support channel, who like to make it very clear, Zenoh can carry bytes, okay, user bytes. It doesn't provide, it doesn't restrict the user on certain types of data. So it's not that, hey, like on DDS is CDR, okay? So you need to carry.
You express your types in IDL and then
IDL
and the serialization, yeah.
Zenoh is raw bytes. For what concerns Zenoh semantics, you send bytes on a given key expression. If you subscribe to that given key expression, you receive that bytes. Mm-hmm. Now, what we introduced with the Z bytes, also a default serializer to facilitate the life of the users. Because most of the times you want to send some easy data. For example, I want to publish an integer or a string or for example, a list of integers. And what we did with this default serializer, it's available on all bindings. Okay, so here on screen we are seeing the documentation for Rust. The same things, we'll have it in C, in C++, in Python, in Kotlin, and so on and so forth. Such a way that in every language, we ensure also compatibility. So if you publish an integer in Rust, you can receive it in Python and decode it as an integer. Yeah. This, of course, is not the only serializer that can be used with Zenoh. This is the default one, is to facilitate out-of-the-box experience for the users.
There is another impact that is super important, let's say for automotive. Yeah. Right? One of the struggles in automotive is you take, as an example, DDS, right? You have to either you certify the IDL compiler and the generated code as a vendor, or the end user has to certify the serializer. And that's a big problem, okay? Because in the technology that they use today, like in SumIP, they were certifying the encoding, okay, in their application. So the reason also why we decided to have serialization for primitive plus, let's say, some container type, is that in our certified version, that code will be certified. And you can use it as is, or easily use it to serialize, starting from certified software, more complex types. That's super important, and I think that's sometimes overlooked. Okay, so that was another important rationale for us to add this support. Yeah. Yeah.
And also this API made really separated from a semantical point of view, the API, what is Zenoh, that current data, and what needs to be done for serializing and deserializing data. And that created a bit of confusion in the past. We look at the feedback, we improve it, and we provide it in all languages. In the past, we also had attachment. So we stabilized it in 0.11, but the API wasn't as ergonomic as we wanted to be. It felt kind of separated, kind of the weird kid in the classroom. And it says why the attachment needs to be different from any other payload.
Exactly.
Why? I mean, but in the past, we have this value that we're treating in a kind of different way, right? So this work about Z bytes was also about to unify all what is the payload, the attachment, the query value, the query payload.
Exactly.
Yeah. So everything now is unified, harmonized across the languages, whether it's part of the payload, part of the attachment, part of your query body. Doesn't matter. You receive data, and you can serialize it, deserialize it exactly the same way in all languages.
Nice, simple, elegant, orthogonal. Right? Yeah.
It feels so nice when you go back to the code base and you just start removing code because you managed to unify everything.
Oh, the best code is the code you
that
never wrote, right? Or that you remove
that
because
you
it's
remove.
not. Yeah, that's the one I like.
A nice. And just a few words about encoding. So encoding, we didn't change really what it meant, but basically we had a little problem about future extensibility about the encoding, that we were basically explicitly enumerating all the possibility. So any modification to that set would have been a breaking change. Okay, and we felt that it was a bit silly to push for a major version for Zenoh just to add some wire level optimization for encoding. So minor change, everything is basically as an API that is string based. So like you have the HTTP metadata, right? That the content type, right? Basically has the same kind of a similar meaning. Now everything is string based. We handle internally when to optimize what we know, what we not do not know. Correct, and the API is free to be extended.
So in other terms, for certain encoding, a small integer will go on the wire, right? Which is what we care about. Yeah.
As well, something that we have been unifying and aligning was about query and queryables, especially compared to what we had for the PubSub. In the publisher, publish data, and subscriber receive samples. Samples contains the data, the key expression, plus some QS information about, for example, the priority or the attachment or the timestamp, etc. And especially as part of the work that we were doing with the storage alignment, we realized that if I publish something and I store it on a database, when I query database, I should be able to retrieve everything that I stored. And we were missing that part in the API. We decided also there to align. So when we reply to a query, we can reply as okay. So like the same way that when you do a put, like, or you can reply with a delete, the same way that when you do a delete, or you can reply an error that says, hey, the query perhaps wasn't invalid. In such a way, you can signal back that something went wrong. And then all of a sudden, replies are handled in the same way that you handle samples on the subscriber modulo, that a reply could be okay on error, but if it is okay, it is a sample. So exactly the same logic, exactly the same work that you do for serialization through the dead bytes that I was seen before. Also there, we aligned and we unified the concepts with a simple API. One addition that we have added, and as a consequence of something that we have removed, is the ring channel. So in the past, we had the pull subscriber. So you could declare a subscriber as a pull subscriber that allowed to retrieve the latest data that was published. So as part of some rework that we did at the protocol, simplifications, harmonization, we realized that the pull subscriber was not much use, was adding a lot of complexity, taking up space.
And you can use query.
And you could use query as well. But if you just had a normal subscriber, you could have exactly from application point of view, logical point of view, using a ring channel to keep the latest data. Because most of the people were using the pull subscriber to, hey, perhaps I've got a long computation, but when I go back, I still want to process the latest data, not perhaps something that was published like 1 minute ago. The ring channel, as the name says, is a way to plug into the subscriber. A ring channel, basically, that keeps the last n elements. That if you always want to have the last, only the last, you can just keep a ring channel of size 1. Or you can decide to have a different size, right, to accommodate some buffering. And all of a sudden, we removed also simplified part of the API because it's always a subscriber, and it's just with a different handler that you can also define yourself.
Yeah, and again, if you have something, a device that goes on duty cycle, because there is a slight difference, right? Just use a query.
Correct. And this is something that we provide out of the box, again, to simplify the life of developers, to provide butters included. But the same kind of approach could be implemented by a developer if it wants to use a different type of channels, custom management for their own samples. You have a way to plug in your own channel or your processing directly inside of the subscriber. And here we are showing the subscriber, but the same things can be done with querybles and get as well. CAPI. CAPI has went through a major rework for a greater benefit. So from a user point of view, we are not changing the logical flow. Okay, the logical flow is still the same, but we have been improving what is the semantics really for the API to make it clear for the user how to deal with data ownership. So when he owns the data, when he doesn't own the data, when he moves the data, when he's loaning the data. There is no built-in support for C. We are used to Rust. In Rust, we've got a borrow checker that does it for you. But in C, we came up with, okay, it will be good to be able to signal the user how you should handle the data and what is allowed or not allowed to do by just looking at the API.
At the signature of the function.
At the signature of the function, or just at the naming of the type, right? So we have been encoding all the semantics inside the namings and inside the signature of the API. So even if you don't look at the doc, because sometimes people don't look at the doc, or sometimes for whatever reason, the docs gets a bit of misaligned or not updated for whatever reason, by looking at the code, if it compiles, you know that it's going to be correct. Then it's always C. You can do dirty things, but if you comply with that, that's the guarantee that we provide.
And by the way, for the newer member of the community, the first CAPI for Zenoh was a regular CAPI, right? And then we had huge discussion internally. We decided to help C programmer to build a software that it's easier to reason about and to write at scale. We made an experiment and we shared with some selected user, right? And their answer was, looks weird at first, but then it's much more productive to use. And so that was really what resolved, right, our internal debate.
Correct. And also, I mean, we let the compiler tell you if you're doing something wrong.
Which is good.
An early catch of the error is always better than going and trying to debug things on production.
Yeah.
In C++, we have been basically reworking the API to especially improve the error handling via either error codes or the exceptions. So sometimes C++ developers prefer to use exception. Sometimes they prefer to use error codes. And there is no right answer here. It really depends on the taste, on the code base you're integrating Zenoh with. And so now you've got the freedom to do both, right? Before it was only error codes. Now you can do both.
Yeah. By the way, something else important to mention is the performance improvement in the C and C++ binding, right? Because of avoiding some copies that,
So coming back to that, well, actually, no, let me jump back, right? Because this is has to do also with this Z bytes, okay? As part of all the PI, especially in C and C++, we were always returning a pointer in the callback for the subscriber, for example. What that implied? Implied that user data had to be. I mean, there was no other option that had to be contiguous in memory.
For C and C++, which was a huge constraint for us. Yeah.
And you need to remember that with Zenoh, we are dealing with network communication. And in all that different topologies, capability of working over layer 2, TCP, UDP, serial, I mean, the MTU is going to be different. We may need to fragment data in Zenoh. So when we start fragmenting data, it means that when we receive data, we receive fragmented data. Either we make tons of copies and keep a lot of reallocations to ensure that data is contiguous in memory, or something that we decide through the Z bytes we can encapsulate, so we are not forced anymore to present a contiguous memory region to the user, but through the Z bytes, through the deserializer or the reader, the user has the freedom to decide whether he wants a contiguous.
So it's like an iterator, essentially,
Right.
in memory. Yeah.
In memory. So has the freedom to say, I really need a contiguous, so the copy will be there. We've got some users saying, hey, why do I need to do a copy now? Well, it's not that you need to do a copy now. We remove it.
Yeah, exactly.
And now you only we only do the copy if you really need it.
Exactly.
Okay.
And then, but I think just not to go too deep, but there are some API that allow you to really iterate through the memory without having to copy. Right?
Correct.
So, yeah, and that's usually the reader API. Yeah. Anyway, we'll cover the details in later because time is running.
Yeah. So I mean, there is a full migration guide that we just posted. So don't have time to go through all the tiny details here, but that's the rationale behind, right? Then in C++, we also improved stream handlers and callback support. Now you can have streams in C++. You can easily chain them. So as you can see, also you can have ring channels and chain, for example, deserialization and all different types of operation you can do now in C++. In Python, not major change, but an addition. So nothing that you need to port in Python for 1.0, but something that we added, and we suggest the user to get to be familiar with that. That if you are a Python developer, you're familiar with the context manager, is to use context manager for Zenoh operation. Like when opening a session, declare subscriber, or for example, declare a publisher or any type of declaration. This ensures that the proper cleanup is done as part of the context manager implementation.
And again, quite some sensible performance improvement in the last Python API.
Yeah. Kotlin API, we've been making the Kotlin API more Kotlin friendly, okay? And as well as to adopt common Kotlin patterns, for example. In the past, we were using default arguments, but it's, the builder pattern for the Kotlin API like we do in Rust, but it's better to use the default arguments that in Kotlin. We also improve it through the Kotlin exception. Before we were returning a kind of a rusty result type that is not very, Kotlin developers are not very familiar with that. It wasn't really as powerful as the Rust result. So we have got built-in exception for Kotlin, so we've been working API to leverage those. And more importantly, something that for people that are coming from garbage collected languages, and this applies also to Python that we just see, session manager declaration. For example, in Rust, it's easy that if you define a variable, you know that if you're using Rust, that variable will be dropped. So the destructor will be called as soon as it gets out of scope. That's not the case for garbage collected languages like Kotlin, Java, and Python. So this change about session manager declarations, so if you declare a subscriber that you got a callback, if you don't need to declare it for whatever reasons, or you don't need to keep it in your life cycle of the application, you are not forced to keep the variable around in such a way that it's not dropped and your subscribers can declare under the hood, and you start wondering why my subscribers start
you'll avoid
data.
some surprises.
Yeah. Plugin loadings. So something that was anticipated at the beginning by Angelo. What's the difference between a router, a peer, client? It's becoming blurrier and blurrier now. So think about that. It's really infrastructure node versus application. But now, something that you can do with whatever application, whether it's written in Rust, in C, C++, so it doesn't matter anymore the type of language that you're using, you can load plugins. Of course, plugins are still written in Rust.
Yes.
Okay, so you still need to write the plugins in Rust, but those plugins now can be loaded through via any application, regardless the language. C, C++, Python, Kotlin, or whatever.
So all of a sudden, you can have storages in your application.
Yeah.
You can have an admin space in the application, which is quite nice also for system management and monitoring.
Or to load the REST plugin for REST API.
Correct. Yeah, so pretty cool.
Protocol. So we have been adding few features on the wire protocol that allows to have some nice optimization. Also, keeping in mind the network overhead that sometimes people paperwise, right? That is about the interest protocol. And this is particularly useful for implementing what we call the right-side filtering. Let's assume that I'm declaring a publisher. And by the way, this is a question that we recently received also on the support channel. Why should I declare a publisher if I can do a session.put? This is exactly why. The declare publisher, as well as any declare something in Zenoh, allows the Zenoh internals and protocol to optimize things.
Yeah.
Okay, so under the hood, you can optimize way better if you, as a developer, you let us know if you are gonna do something that is repeated over time, so it's not one shot. That's an important distinction.
It's very important, exactly.
Okay, if you just want to do
a few
put, that's okay.
Don't bother.
But if you know that your publisher is going to publish data over time, over and over and over, it's better to declare a publisher because we can optimize things under the hood. And this update that about the new interest protocol implements a nice feature that is right-side filtering. What does it do? If you, for example, you're a client, you connect to a router, say, hey, I want to declare a publisher. Please let me know if there is any matching subscriber. Okay, the router through this interest protocol. So basically, you declare your interest about knowing about available subscription. Yeah. If at least one, right? The router will let you know whether there is some or none. And if there is no data, I mean, you can basically drop your data locally without even sending on the network, because you know that there is now this protocol in place that tells you that, hey, there is no subscriber at this very moment. It's useless to send it over the network. But as soon as at least one subscriber comes in the overall system and there is one matching subscription, this new mechanism in the protocol will, for example, the router will tell the client, say, hey, now you've got at least one matching subscriber. Yeah. Now, if you send data over the network, that will not be wasted. So you'll have something that is interesting. Yeah.
And I think it's important because there are really two use cases, right? Even before, we could avoid sending data, but the cost was to propagate all the subscription. Yeah. And this allows you to decide whether exactly you want, but potentially you could say, I'm a very constrained link. I'm dimensioned to send one message every hour. Just don't bother me with any declaration, right? I have no intent, okay? I will publish anyway, right? So that's very important because allow us to be very granular.
Especially for the embedded.
Exactly.
Because what we had before, that declaration were propagated, were pushed down.
Exactly, right? And sometimes you don't want.
You don't want because perhaps your embedded device, you don't have enough memory to deal with that, or processing power, or maybe just battery life.
Exactly, right? For whatever. Your dimension to publish in any case, right? So, yeah. So that's a quite powerful extension of the protocol.
And then let's touch the bloody Tokyo porting that we finalized in 0.11, okay? But we could argue a lot about, the Rust async landscape, the difference between executors and API, etc. The reality is that even if the porting per se from API perspective wasn't so difficult, okay, because that is handled by the Rust async trait, etc. The actual making it work at the same level as before,
and the semantics, right?
With the same semantics, with the same guarantees, that was a ton of work.
Yes, because the behavior was really different.
Yeah. The behavior was different, right? So the API was pretty similar. The behavior is really different, and
extremely different.
Extremely different in some cases, right? And what happened after the 0.11 that we also start having some users, especially for the bridge, right? For robotics, say, hey, I've got my sensor that is publishing at a given frequency, for example, 1 kilohertz. And all of a sudden, before I was publishing at 1 kilohertz, I'm receiving 1 kilohertz. Now I publish at 1 kilohertz, and I've got some delay before.
Well, they were receiving just one sample on the DDS side, which is another effect, right? That's a combination.
DDS was overwriting
the history.
Latency.
And long story short, this was due to how Tokyo manages timing, especially granularity of timer internally. Because in Zenoh, everything boiled down, right? And on these slides about batching and jitter. So in Zenoh, we've got a system mechanism that is called automatic batching. So if you have multiple messages that need to be sent on the same link, and if those messages are coming fast enough
and are small enough,
we can batch them together in such a way we can further reduce the network overhead. And as a consequence, we reduce the network overhead, we also increase the throughput. Okay. Because of this difference in timing, I mean, we were batching a bit too much.
Yes.
Okay, so all the internal timing was went off. So we analyzed, investigated what was reported by the users, and we have been reworking part of the batch mechanism, accounting for the limitation, constraints, and peculiarities of the Tokyo runtime. Now, we improved also that compared to the past. We tested up to also 10 kilohertz, 100 kilohertz. We keep doing with a good pacing. Now, if you really are in extreme throughput scenario, then batching does really all the magic to bring you to 1 million messages per second.
And you get exactly the appropriate frequency that you're publishing, as we
you
show in the graph here. Everything is flat, so frequency keeps constant.
Very good. Okay, so Julien, what are we cooking for Zenoh RMW?
So for the Zenoh RMW, well, first, what is RMW? Because a lot of users are not familiar with robotics. So actually, in ROS 2, the middleware used for a lot of robotic application, it's a modular architecture. There are several layers for your robotic applications. So robotic applications are based on various APIs, C++, Python, Java, and so on, which itself is based on a C API, which implements a lot of common feature for robotics, and itself based on RMW. RMW standing for Robotic
ROS
middleware. Exactly. So that's really a wrapper, which was originally built above the DDS specification. So it supports several DDS vendors: Cyclone DDS, Fast DDS, Connex DDS, and so on and so forth. But recently, as you explained, there was a survey to find an alternative middleware to DDS in some use cases, and Zenoh was selected. So with the help of Intrinsic, actually Intrinsic did most of the job for this. We were supporting them with specific feature required in Zenoh. They developed RMW Zenoh. You have the GitHub repository here because it's already available. It's already quite well tested. And it's based on Zenoh C, which itself is based on Zenoh in Rust. So implementation is still in progress, but now it's already usable. We test it with...
it passes essentially, the CI is essentially
it's essentially
all green,
yes, with just a few exceptions with some specificities of DDS which are not yet available in Zenoh.
But the 4 test failing or something like that, right? So marginal.
But we already made some real robots or simulated robots to run with RMW Zenoh, and also benefiting all the feature from Zenoh, right? With regard to connectivity, connectivity to the cloud, and so on. So how was it done actually? First, about data encoding. So ROS was using DDS, so it was using DDS CDR. There was the full code generation chain, which is already used in a lot of ROS projects. So the nice thing with Zenoh is that it can support any encoding.
Doesn't care, exactly.
So they can keep their existing CDR encoding and keep the code generation they already have.
And if they want to change it one day,
they could.
Exactly. Protobuf, whatever, yes.
ROS is using, of course, PubSub. So the PubSub in ROS is naturally mapped to the Zenoh publication and subscription. With a tiny advantage, or a tiny change is regard to the transient local implementation. So transient local is for a subscriber to retrieve past publication. So in Zenoh, we map this into an extension to Zenoh, which is named Publication Cache and Querying Subscriber. And it fits very well. And now transient local is also supported with RMW Zenoh in an efficient way. Service, server, and client. So ROS also has this concept of service. You can call a service and the service will reply. It naturally maps to Zenoh queryable and querier. And then on the upper layer, you have actions and parameter, which are kept untouched because they are just based on the pub sub or service layer. The last point, quite important, is the ROS graph. So what is a ROS graph? It's for each component in ROS, each node, when it declares a service, a publisher, a subscriber, an action, it can be discovered by other nodes in the system. So there is a complete discovery of all endpoints, all interfaces for each node in our system, which Zenoh doesn't provide by default, because we want Zenoh to be scalable, and this kind of discovery usually doesn't scale very well in very, very large system. For robotic, it's quite small, relatively small, let's say, so it can be scalable. So ROS graph have been mapped to the Zenoh liveliness token. So what is a liveliness token? It's just a key expression, so a string that you declare and which is attached to the Zenoh session, so to the liveliness of your program, let's say. So it means as soon as your program crashes or is disconnected, all other nodes subscribing to the liveliness token will detect that the interface, the publisher, the service is gone. And that allows the ROS graph to be implemented.
And again, you can either get a publication, in other terms, or a subscriber that is notified, or you could query, which is super powerful, right?
Absolutely, yes, because all of a sudden, you don't necessarily need to be overwhelmed with all the discovery at a time. You can query when you want the discovery you want.
Exactly.
And that's quite powerful to scale, also in robotics. With regard to deployments, so one of the issue ROS2 people had with DDS is the automatic discovery of your UDP multicast. So, for instance, in education, when you have a lot of different robots in the same classroom, all connected to the same Wi-Fi, all the robots by default are discovering each other using the same topics, and this creates a mess, and usually it breaks everything.
What is the problem? When automatic becomes accidental, right?
Yes.
When we have accidental discovery, then who the hell is driving my robot?
Absolutely. So a lot of users were actually plebisciting the previous behavior from ROS1, where there was no discovery by default. You rely on a ROS master to perform all the discovery. And Zenoh has the flexibility to offer this back to ROS2 user with the router. So the router acts here by default in ROS2 as a deployment service, a discovery service. Sorry. So you need to start the Zenoh router, and all the nodes, the ROS nodes, will connect to the Zenoh router, and the Zenoh router will do the gossip protocol, so forward all the endpoint location to each other nodes. And the nodes will be able to establish direct peer-to-peer connectivity amongst each other. So by default, the router listens on any interface on port 7447, so it can be also accessible from the external. And each node will connect only over the loopback to the local router. And the connection will be established over the loopback. But the Zenoh is a router actually, so it can also route communication over the Wi-Fi. And this is very useful also to configure in only one point all the connectivity of your robot. You can configure the TCP, the TLS with the key certificate, the quick. And the other benefit is that you have less connections, so less overhead. We have a powerful batching. So if you have several nodes publishing a lot of small messages, the router can batch all together, improving the throughput of the
transparent compression.
Transparent compression can be activated. There is a smaller surface of attack because there is only one or two ports open, depending how you configure your router. And moreover, you can configure access control and downsampling.
Exactly.
Meaning, for instance, that over Wi-Fi, you will downsample high-frequency publication, which can kill your Wi-Fi.
So, do you know that there was the India Autonomous Challenge just a couple of days ago? I believe the Italian won again.
Again?
I think Polymi won again.
Yeah, of course. They're very good.
And so, why don't you tell your stories with the India Autonomous Challenge?
Yes, actually, that's a feature that we started to develop for the very first edition of the India Autonomous Challenge with the very first DDS bridge at this stage, right? Because in Autonomous Challenge, the bandwidth over the track, the racetrack, is very limited.
It's a curb.
It's a curb. It's not really as powerful as a Wi-Fi, right? Because it's long range. And moreover, there is only one for all the teams. So they need to share the bandwidth. So they need to really control fairly how the bandwidth is shared among the teams. And of course, they publish a lot of data inside the car. They need to control some of the data, but not at the frequency which is published inside the car.
And with DDS, everything was getting out. First point.
There was no choice.
Second point was getting out at the wrong frequency, right?
Exactly. Yes. So we implement the very first down sampling feature in the Zenoh DDS bridge
Plugin,
in the plugins a few years ago, and now it's available in Zenoh Router for all robotic application using RMW Zenoh.
And in fact, two Zenoh applications.
Two
right?
old Zenoh applications,
exactly.
right.
Which is is a very good integration pattern, right? It's a way, of controlling a boundary of application and imposing it.
Yes. So RMW Zenoh in current version is not yet port to 1.0.0. The pull request is in progress. Actually, it's already almost done. It's just in review, in code review right now, so it will be merged pretty soon, we hope. And yes, it will bring all the 1.0.0 feature to all robotic users.
And we'll be bringing
with
shared memory too,
So with shared memory,
yes, will
also
be quite cool.
Shared memory with custom allocator will be also available for robotic
which
applications.
is quite important use case also for when you use custom hardware or video cards memory.
Absolutely. Yeah.
Great. So next steps. So we are in release countdown mode, right? So as you've seen, we've been releasing one beta per week, and we'll continue to do that for the entire month of September. And we'll, literally do 1.0 the last week of September. Now, I think the community has been terrific, right? Because they tried, they've given feedback, they've found bugs. We've been releasing 1.0 since what, June? Since June.
We released the 0.11 in May, and straight after we already had a big batch.
Exactly,
for the 1.0.
We started doing,
for all the alpha, getting out, getting feedback, getting testing.
So thank you very much, because it's great.
So it was amazing.
We've addressed, I think, through the comments we have further improved. So that's great, and that's the value of an open community. And I think we will all celebrate one way or another together. This big event. For what concerns ZettaScale platform as a service, so the ZettaPass and our offline tool, we need to get Eclipse Zenoh out first. 2 weeks after, we'll release them. And I guess that's it. So we're overrun of course, always. We overrun a little bit, but there was a lot to cover already in this intro webinar. So let's let me check now. Let me stop sharing for a moment my screen, and let's look at questions.
Question on the right in the chat, maybe.
So down here.
Yeah.
Okay, give us a moment to scroll. So will the C# be supported in V1.0?
So we don't have the support yet for a C#, right?
So that will be a post V1.0. Absolutely. And the current C# doesn't even work, right?
It was in based on 0.7.
Yes, it was based on an old version, and we didn't have time to port it.
But again, this is one of the programming languages I think on our list is next, because it's important for industrial automation, where we have more and more use cases. It is important for some robotic simulator, for gaming. Yes, so that will be the next one. So if you want to join up, we're always happy to get some contribution. But in any case, we'll be next up, and I'm pretty likely you will see it on the roadmap that we'll publish for the post V1 releases. Still scrolling.
So image raw. Can you use image raw to stream images or compress image message type in ROS 2? So, well, actually, yes. As we said, Zenoh can transport any bytes, right? So as soon as your image is published as a byte array
But again, I think there are really two ways of doing this, right? So if you're using ROS API, well, you have no control.
ROS chooses.
Right. But even from ROS, you will be able to recover a Zenoh session. Okay. In that case, for instance, you could even use potentially shared memory to transfer this image. Okay, and this is something that we are discussing quite a bit with the ROS team, because there are some use cases in which today, as you know, the zero copy API for ROS, and in fact the loan API as they call
Loan
it,
API,
it's very error prone, and it doesn't fit well with the Zenoh model either, because if you look into the Zenoh share memory, our model is quite different. We provide you with share memory provider that then are used by share memory allocator that take memory from somewhere, right? The default allocator is for POSIX, but you can do it for whatever you want. And then you can allocate buffer out of this share memory allocator. Whatever you put in the buffer, we don't care. At that point, that becomes a buffer that you can send, like a Z bytes, like Luca showed before, that you can send with a put. And then the Zenoh trickery comes into play, whereby all application that Zenoh can detect are on the same share memory domain, and that is done through an handshake while opening a session, will receive just some meta information that allow you to access those bytes, okay? And everything else will receive data sent across the network, okay? Now, this is the model we like because it allows you for true zero copy. All of a sudden, I can have something filled by hardware that I take, right, and then I send over with true zero copy. The current ROS model is limited by how DDS work, because in DDS you always have serialization, and that makes it impossible to have the kind of zero copy that we want. That I think is the true zero copy. Voila. So
yeah, but anyway, by default right now, RMW Zenoh is working with compressed image or raw image.
Of course.
It's just that it's not optimal with regard
Correct.
to shared memory usage.
Absolutely.
That could be used.
Yeah, but that's another way in which, if you have really high performance requirement, you could, if you have Zenoh as an RMW, that you could exploit. What is the roadmap for authentication beyond user password? Do you want to take this?
Yeah.
Luca.
So beyond user password, we already have working TLS for either server side or mutual authentication.
Yeah.
So seeing the question is quick TLS supported is server side at the moment.
No, we have both.
Yes, you're right.
We have both.
We have
both.
yeah. Added for
because
quick,
we use it on the platform. Yes.
Yeah. So we also for quick we got multiple authentication for quick. So token based is not something that we've been discussing or envision, because I think it's kind of authentication that works well in the cloud paradigm. It has a big impact on what will be on Zenoh, but it's something that we never discussed deeply.
We could consider it.
Yeah, I'm happy to learn more, Tiago. Yeah. So will the Zetta? So Robbie, no, the Zetta offline tool won't be open source, because we have somehow to also survive, and that's one of the way in which we try to monetize all the work that we put in the open source. So that's really an offline version of the function that we have as part of our pass. But then is the model that we try to have is always reasonable, right? So making sure that we build great technology that is affordable for everyone. So if you are interested, by the way, in having an evaluation, we will be releasing a preview probably in 2 weeks. So reach out, and I will be happy to give you an evaluation version so that you can provide feedback and play with it. Let's see.
So there's another question that slipped in between. But will not be shared zero copy on one router. Also, if the compressed image is used, suppose it can be decoded by a CDR on another. So share memory. I can take the share memory, then you cover the rest. Share memory to work, you will need to be in the same memory domain. So if you're going out of the robot over the Wi-Fi, of course, that will not be share memory.
Correct. Although, right?
There are some catches, but it's not
correct in general. But we have been discussing, right? For instance, about RDMA. Yeah, it's not there yet. That's something we want to put in, but not sure if that's your use case, because you don't do RDMA over a one either.
No, usually you don't do over a one. It's something limited in a data center or kind of closed wired domain.
Yeah.
So on the other question, if the compressed image is used, I suppose it can be decoded via CDR on a non-ROS end. Absolutely, yes. If the compressed image is sent via ROS, ROS will encode it with CDR. So any Zenoh application able to subscribe to the publication will receive it as a CDR encoded payload and will just be able to decode it.
Yeah, I forgot to click on the question. Let's leave this. So we don't see any. Let me scroll again in case, because we had like some out of order question insertion. Just to make sure that we are not missing any. So this was addressed. This, let's see. This, thank you, Robbie, for the appreciation. So that was addressed. This was addressed. Yeah, I think we addressed them all.
Yep.
Then, well, guys, thank you very much. It was a pleasure, like always.
Yes.
Right. Thank you to all of you, and see you in 1 week. Ciao.
Goodbye.
Bye-bye.
Bye-bye.